Good morning, NetI 105 students. This is Mike McGinn, your online instructor, and this presentation is over Chapter 5, Ethernet. In this chapter, we will talk about the Ethernet sublayers and the major fields that make up a frame, which is the PDU of the data link layer. We will talk about the significance and the characteristics of the Ethernet MAC address. We will talk about ARP, which is really important in a network, and how ARP requests impact the network and host performance. We'll talk about some basic switching concepts, and we'll get into a little bit of the hardware and talk about fixed configuration versus modular switches and how to configure a layer 3 switch is at the end of the chapter. Okay, so jumping right in section 5.1.1.1, we talk about the LLC and MAC sublayers. The LLC sublayer, which stands for Logical Link Control, is the upper layer of the data link layer, or layer 2 in the OSI model. The data link layer is primarily your hardware, or your network interface card software driver. So, as you know, if you've ever installed a network card, you put the hardware in, and then there's usually some sort of software you have to install so that the operating system knows how to communicate with the actual network card itself. This is basically installing the components that allow the LLC layer to function. What the LLC layer does is it manages communications between the upper layers of the OSI model and the lower level of the data link model, which is the MAC sublayer, which is actually part of hardware, and the physical layer, which is the actual media that the data is going to travel across. So when we talk about Ethernet, we're talking about the bottom two layers of the OSI model. And these are defined by two standards, the IEEE 802.2, which defines the data link layer and is independent of any hardware. And then 802.3 defines the MAC sublayer, which is hardware specific, or involves the actual integration with the hardware, and the physical layer. Slide 2 on 5.1.1.1 does a nice job of kind of laying out how this all works and where the standards fit in to these particular scenarios. You'll also note that they list here the different speeds that Ethernet is available at now. It can go anywhere from 10 megabits to 100 gigabits per second. Typically what you will see in networks, in local area networks, is you'll see 1 gigabit and 100 gigabit, and a little less often 10 megabit on some legacy equipment. The 10 gigabit, 40 gigabit, and 100 gigabit are mainly for Ethernet backbones or Ethernet broadband. But I suppose in large campuses you could see those larger bandwidths in production. Okay, so a little bit more about the LLC sublayer. The LLC sublayer, again, handles communication between the upper and lower layers, and it's typically network software. The network LLC sublayer is the network protocol data. It takes it, and it's just typically an IP version 4 packet, and adds control information to help deliver the packet to the destination node. The LLC is used to communicate with upper layers of the application and transition the packet to the lower layers for delivery. So you can think of this as kind of the bouncer at the door between the physical world and the virtual world. Now the MAC sublayer constitutes the lower layer of the data link layer, and MAC is implemented by hardware. And MAC stands for Media Access Control, which would make sense because that layer is basically responsible for taking whatever the LLC gives it and laying it on the pipe, which is the physical media. So in 5.1.1.2, we dive into the MAC sublayer, and basically the MAC sublayer has two important responsibilities. It performs data encapsulation, which means that it's taking the packet, in most cases, from the upper layer, and it is encapsulating it into what is called a frame. And then it puts header and trailer information into the frame that does things like frame delimiting, which is used in synchronization between the sending and receiving node, telling it when a frame begins and when it stops, etc. It does some addressing. It actually assigns the source and destination MAC address to the frame so that it knows where it came from and where it's going. Remember, a MAC address is unique to that network address card, and it's probably pretty easy at this point to understand where it's getting its source MAC address, but it also assigns the destination MAC address. So you might ask yourself the question, well, how does it know that? Well, the answer is coming, and that is in ARP, a little teaser for you. The last function that data encapsulation does is it actually puts on the trailer of the frame a CRC field, which stands for cyclical redundancy check. And basically what it does is it calculates a value that when it builds the frame, and then that is based on the contents of the frame. And then when the receiving node gets that frame, it recalculates the CRC value, compares them, and if they're the same, it assumes it's a good packet. If it's different, it assumes that a good frame rather than a good packet. And if they're different, it assumes that that frame is corrupt and discards it and waits for a resend of that particular frame. Now, the media access control is the other responsibility of the MAC address layer, and that basically controls the frame placement on and off the media and also handles media recovery. So when we talk about media recovery, we're talking about the technologies we've talked briefly before in earlier chapters, such as the contention-based technologies such as CSMA and CSDA type of things that handle collision detection or avoidance. Okay, in 5.1.1.4 we talk about the MAC address itself. Now the MAC address is burned into ROM on the actual network interface card or network interface function of that piece of hardware. So again, every Ethernet capable device, whether it be a smartphone or a notebook or a desktop computer, etc., has a MAC address assigned to it, and it is unique only to that device. That device is the only device in the world that has that specific MAC address. The MAC address is a 48-bit binary value, and it's basically broke up into two parts. There's the first 24 bits is the organizationally unique identifier. This is the part that is unique to that particular vendor. And so basically, based on the first 24 bits of a MAC address, you can actually determine who the manufacturer of the network card is, if you don't know by any other means. You can actually search by the first 24 bits, and it will, on the internet, and it will tell you who the manufacturer of the card is. The vendor assigned part of it is the NIC, the interfaces, the things that are particular to the functionality of the card itself. But the organizational unique identifier is what uniquely identifies that particular card to any other card in the world. Moving to 5115 frame processing. The MAC address, it's often referred to as the burned in address because it's burned into the ROM or the read-only memory of the NIC. So on modern PC operating systems and NICs, however, it is possible to change the MAC address in software. This is useful in attempting to gain access to a network that filters based on a burned-in address. I guess this is, you consider this a potential hacking capability that a lot of network cards have. MAC addresses then therefore are assigned to all types of network devices, as I said, and they show some different formats that you might see of an actual MAC address. It's basically the same MAC address notated in different ways. So the little animation that they show here does a nice job of kind of helping you visualize what is happening when a frame is actually getting built and sent and the like. So in 5.1.2.1 we start talking about the actual Ethernet encapsulation and the fields that are contained therein. On slide 2 of this particular page, they show a couple different formats of a frame. One is an 802.3 standard frame, another one is an Ethernet 2 standard frame. So you'll see both out there. So the 802.3 Ethernet standard has been updated several times to include new technologies, and the Ethernet 2 frame is an older standard. But one thing you'll find is there is several fields that you want to keep an eye on. There's something that's going to tell you the frame is starting, which is usually the preamble and the starter frame delimiter. And then you have a destination MAC address, a source MAC address, and a length to tell you the length of the payload that's about to come, whether it be 46 to 1500 bytes, and then the header and data of the 802.2, which remember the 802.2 is the data link layer, okay? Or I'm sorry, the LLC layer. That's your data payload. That's what you're actually encapsulating in the frame. And then you have a frame check sequence that is basically your CRC check to make for error correction, etc. Again, same similar thing with Ethernet 2. A couple things about Ethernet frame size that you need to be aware of is for one thing, a frame has to be at least 64 bytes long and can be a maximum of 1518 bytes. If you have a frame that is less than 64 bytes in length, it's usually considered a collision fragment or a runt frame and is automatically discarded by receiving stations. This can happen on a network for various reasons, collisions, etc. But if it's less than 64 or it's greater than 1518, it's considered a bad frame and is discarded. A frame shorter than 64 bytes is considered a runt by most vendors. In one of the revisions to the 802.3 standard, I believe it's 802.3 AC, it was extended by allowing frame sizes up to 1,522 bytes. And what they did is they added 4 additional bytes to the frame, which is the 802.1Q VLAN tag, which consists of 4 fields. And what this does is this helps, it basically tags that frame for priority through the network. If you think about the different types of traffic that we have on a network, voice being a good example, because voice traffic needs to have high performance, although it's low in overhead on the network typically, it has to have high performance, otherwise you get poor voice quality or jitter or an echo perhaps, and the quality of the voice call will suffer. So the 802.1Q tagging came into play to basically flag that particular frame as being a high priority flag. Through software and switch configuration, you can tag other types of traffic as well. You can tag, for example, a certain application's frames to be of a certain tag so that it gets higher priority through the network as well. Media as an example, if you're streaming movies or something like that. So in 5124 activity Ethernet frame fields, you need to own that because you will be tested over it. Being able to know what is what on that particular exercise will do you a lot of good. In 5.1.3.1, it's just a little bit of math. They explain to you that you can translate MAC addresses into decimal, binary, or hexadecimal. So not real heavily tested on. It's not like you've got to do any conversions that I'm aware of. I could be wrong about that, but I think it's important that conceptually you have an understanding of the relationship between decimal, binary, and hexadecimal numbers. They talk about the hexadecimal representation of a MAC, the representation of a MAC address. If you do an ipconfig/all on a computer, it'll tell you what the MAC address is of the NIC. It's called the physical address, and they show an example of it right here. And you can see it notated with dashes in various text, or with colons, or with periods. They all mean the same thing. It's just different ways of notating a MAC address. There are some special MAC addresses. There's a unicast MAC address, and a unicast MAC address is the unique address used when a frame is sent from a single transmitting device to a single destination device. So that's typically the type of MAC address that you'll see. It's basically where did I come from and where am I going? So I came from, I'm going to destination MAC, AC-28, which is your server, and I came from CE-53, which is my computer H1. Now the broadcast address is a little different, and when you see a destination MAC address of FF, well, all FFs, and the source MAC address being from a single computer, basically what that is that's a broadcast frame. That's a frame that the source host is determined needs to send out to all destinations within a host group. So so that's what a broadcast address is. So once again, a broadcast group would be all the computers that are on a particular LAN. So on the 192.168.1.network, a broadcast address would go to all computers in that particular network. Now the multicast address is just like a broadcast address, only the number of groups that it goes to, or number of computer hosts that the frame is sent to, is a subset of the entire network. And the destination MAC is a special MAC address that has been assigned to that particular group, and it is able to determine what computers it's supposed to go to. So in lab 5136, there is, I'm not sure if this is assigned to you. I don't have the course calendar in front of me, but this lab on viewing network device MAC addresses is a pretty pretty good way of getting yourself familiar on how to, you know, actually look on a network, find a frame, break it apart, see what it is, etc. Okay, so as we get into 5.1.4 section of the chapter, this is where it gets kind of interesting, because this is where we actually figure out how it all really works. And how it all really works has to do with the relationship between the MAC address and the IP address. So the way to think about the MAC versus the IP address is that the MAC address is the physical address of that particular device, whether it be sending or receiving device. The logical address has been a assigned address to that device that is logical based on the location of where it's at. Both the MAC and the IP addresses work together to identify a device on the network. So, you know, if, for example, if all we had was MAC addresses, you know, and let's say you're in the United States and you want to send to a computer in Greenland, and all we had to work with MAC addresses, you know, can you imagine the lookup you'd have to find to find that, you know, to figure out what that MAC address is would be nearly impossible. You'd have to send a message out to every computer in the, essentially in the universe, or every device in the universe, and say, hey, are you MAC address whatever? And they would have to respond yes or no, and you would have to, you know, process all those acknowledgments until you found the destination. Well, obviously the overhead of that would be overwhelming, and so that's not a viable option. The IP address gives us a little bit better way to deal with that, because it allows us to actually route our requests to find particular devices across the IP universe. So in 5141, they kind of talk about that relationship. And in 5142, they talk about the end-to-end connectivity from MAC and IP. So, you know, when a frame gets built, what's actually in the contents is, as we've discussed, is the destination and source MAC addresses. And then also in the payload of the packet, the IP packet, you've got the source IP address and the destination IP address. These four things together really make it all happen. The destination IP address is usually the IP address of the destination host's gateway on the internet, or in a local area network, it's just simply its IP address. And the source MAC address may be that device's MAC address, or it may be the MAC address of a router or whatever that it needs to be able to get to that particular IP address. So that's kind of how these things two work together to get to where it needs to go. And you'll see illustrations of that as we go through the chapter. Okay, and now we move into 5.2.1, which is ARP. Now recall that in order for a frame to be put on the media, it has to have a source and a destination MAC address. Well, as I mentioned earlier, we always know the source MAC address, but we may not necessarily know the destination MAC address. So there are essentially two different ways that we can obtain the destination MAC address. Both utilize what is known as an ARP table or an ARP cache. So on a computer that you are working with, in RAM on that particular machine is a dynamic table called the ARP table, or the ARP cache. And what that is it's a map, and it basically maps a destination IP address with a MAC address. So, and then, IP addresses can be determined for a destination through mechanisms like DNS or domain name resolution, etc., to be able to get that. So it's much easier to get an IP address of a destination device than it is to get a MAC address. So to maintain this ARP table, there's really two ways to do it. One is that you can simply monitor all the packets or frames that are flying by your segment on the network, and if you do not have that particular IP address in your ARP table, you obtain it, you populate the ARP table with its corresponding MAC address from that frame that happened to fly by your network segment. The other way is that if you need a MAC address and you do not have it in your ARP table for that particular IP that you're trying to send to, IP address that you're trying to send to, you can send out a broadcast message to all the devices on your network, and that says, hey, I'm looking for IP address 192.168.1.7, for example. Are you out there? And what happens is it's 1.7 sees that broadcast and then sends a message back that says, yeah, I'm here. And when it sends it back, it's got that MAC address with it. So therefore, the host then can update its ARP table, and then it can send unicast messages from there forward. So what ARP does is it resolves IP4 addresses to MAC addresses, and it maintains the ARP table, as we just discussed. The ARP process is illustrated in this animation here that does a pretty good job of explaining what's happening. And so here you see the ARP request going out, and then you see the appropriate device sending the device back, and then unicast traffic just begins. So that's pretty straightforward. Once you see it in these graphic or these animations, it does a good job of explaining things and showing them how they work. And there's another step-by-step, illustration of what's going on with that. So this is something you need to take the time to understand thoroughly. Now the ARP role in remote communications is that when your destination IP is not on your segment, it's got to go out through the gateway, and that gateway has an IP address. So so what happens is when it builds the frame, it basically is going to put in the destination MAC address, the MAC address of the gateway, not of the computer you're trying to get to. And as the frame travels through the internet, it gets different destination frame tagging as it goes from one hop or one segment of the internet to another, until it finally gets to the local LAN that that destination host is on, in which it will then ultimately get its unique host MAC address. So so that's ARP, and ARP can create some problems. For example, if you can have ARP broadcasts or storms that can overhead create too much traffic on your media and causing network performances. It's possible for ARP messages to have false or incorrect MAC addresses and will then hijack frames that use that address, which is called spoofing. That's kind of a form of hacking. There are some security concerns with ARP that you have to be aware of, and mitigating configurations, settings you can take to relate to that. So to mitigate ARP problems, there are a few things with you can do with Cisco switch security technologies. Don't really get into them too much in this course, but there are things, like I said, you can do to alleviate some of the security concerns and the performance concerns that go with ARP. On most small local area networks, it's not an issue. I've rarely seen ARP be a problem in a properly engineered network. Okay, finally in 5.3.1 section of the course, we actually get into how switching actually works. And there's a layer 2, on a layer 2 switch, or I should say a switch, a basic switch is a layer 2 device. And what that means is that that device, that switch, has a MAC table in it. And what it is it's a map that maps a MAC address to a particular port, or MAC addresses to a particular port, so that it knows that if I have a frame that comes into my switch that is for a particular MAC address, I know exactly what port to send that frame out of. I don't send it out all ports, unless of course it is a broadcast frame, because it's an ARP request. Then I would send it out all ports except for the port that the frame came in on. That's kind of how a switch works in its very basic form. And there are some settings on a switch to be aware of. There's duplex settings that you can set on particular ports. And for example, duplex is whether or not it will it sends traffic in one direction at a time, or in full tap duplex, it can send traffic both ways simultaneously. Some old legacy devices sometimes require that half duplex. On most modern networks, though, it's not typically an issue. Auto MDIX is another setting you can set on a port on a switch, and basically what that does is that it basically auto crossovers a connection between two like devices. Remember, if you from earlier in the course when we talked about it, if you have two switches and you plug them in, um, you would need a crossover cable unless the ports you plugged into were set to auto MDIX, which is the default on most switches, so you don't really need to configure anything. So straight through patch cable will work between two switches. And so that's what they're talking about with auto MDIX. Then they get into different types of forwarding methods of packets. In other words, what does it do with the packet before it forwards it on? A store and forward switch receives the entire frame first and then basically checks it all out, makes sure it's a good frame, and then looks up the destination address, which determines the outgoing interface, and it's forwarded out that port. Whereas cut through basically starts to forward the frame before it's even entirely received. At a minimum, the destination address of the frame must be read, and then the frame starts to get forwarded, or gets laid out on the media out that outgoing port. So there's some animations on the store and forward switching and also on cut-through switching that explains that. And there's an activity on frame forwarding messages that you want to look at. I guess one thing I'll mention to you about those two types of things is, well, what's the advantage of one versus another? Well, you know, the store and forward you would think would be better in terms of making sure that you don't have any bad frames getting thrown out the output ports, which is true. However, it puts a lot more overhead on the switch, so a cut through is putting the burden on the host to discard frames that it doesn't need, whereas store and forward puts the burden on the switch itself to basically filter bad frames, etc. I also talk about memory buffering on switches, and what you can do is you can set a particular port to have certain buffer of frames that are stored in queues, uh, and then you can have shared memory, which is just a big bucket of memory that all the ports use in common memory. Generally, most switches are set up for shared memory unless you've got a specific situation where port-based memory would be required. And then in 5.3.2, they talk about fixed versus modular switches. Fixed configuration switches, basically features and options are limited to those that literally come with the switch. So not much flexibility there. Those are usually less expensive switches. Modular configuration switches are those that come in a chassis format, and you basically accept the line cards that you need for the different types of media that you need to plug in, etc. There are also stackable switches, which are basically multiple switches that link together and become one virtual switch. And that's a pretty common technology that you'll see out there, as well as the modular configuration switches. In small networks, you'll see fixed configuration switches. Although fixed configuration switches are that have no options are very rare. I suppose a cheap workgroup switch you'd pick up at Walmart would be considered a fixed configuration switch, like a little 5-port workgroup switch. But most of your business class switches have at least one um, module slot that you can purchase optional 10 gigabit Ethernet or fiber optic modules for that particular switch. So in Cisco switches, especially your Catalyst series switches, you have a lot of options in terms of different modules, and they have basically in the Catalyst world they're called SFP modules, small form factor pluggable ports that are what that stands for. And there's a list here of the different modules. This isn't something that you need to memorize. It's basically just marketing material, if you will, on the different capabilities of Ethernet switches. Then finally in the chapter we talk about layer 3 switching. Well, we haven't talked much about routing yet, but basically what a router does is a router based on IP address determines which port in that router it should send that uh, packet out or that frame out, ultimately a frame out of that router. A layer 2 switch is strictly based on MAC address. It maintains a MAC table and basically based on the destination MAC, it determines what port to set out. So in a layer 2 switch, an IP doesn't matter. In a layer 3 switch, though, a layer 3 switch basically acts the same way as a router, where it can determine what port it needs to go out of based on IP address as well as MAC address. So where that comes into play is that you have the ability to basically create a virtual switch within one physical switch. These are referred to as VLANs. So you might have a VLAN 1, which is a network for engineering, and you may have a VLAN 2, which is a network for accounting. And even though they're on one physical switch, in the layer 2 world, if there's two VLANs configured on that switch, nothing on VLAN 1 is going to be able to see VLAN 2. Well, if it's a layer 3 switch, you can create basically routes that say, okay, if I'm on the engineering LAN and I want to be able to print to only this particular printer on the accounting LAN, on a layer 3 switch, you can do that because you can route traffic from one virtual LAN to another. So that's one application of a layer 3 switch. So what layer 3 switches are doing is they're reducing the need for routers in your campus networks. Where you see routers are usually now in the perimeter of your network where you need to hop to different media like different media from a service provider. So you see routers at your perimeter more so now and less in the actual LAN environment because of the introduction of layer 3 switches. So layer 3 switches are really combined layer 2, layer 3 switches, but um, uh, they do provide you a lot more flexibility and a lot more security within your network because it does allow you to more easily segment your networks within your organization for security reasons, but still allow the capability to route traffic between those specific networks. And you control that routing. Whereas in a layer 2, pretty much if you're plugged in, you can see the world. Or if there are VLANs, you can see only your world, but you can't see the other, period. Layer 3 allows you to get by with a lot more flexibility. Okay, so you got basically a packet tracer to do in this particular chapter, I believe. But I would encourage you to do some of these other exercises as you've got time. They're really good and they really help you understand what's really going on at layer one and 2, and even a little bit in layer 3 as you move through this. And this is one of my favorite chapters because it really, in my mind, opens your eyes up to how this stuff really is happening out there on the network and understanding it. And it's going to allow you to troubleshoot in the future and to be able to identify where root causes are in your network if you ever have to troubleshoot it, whether it's your home network or if you're, an infrastructure engineer in a larger network. This information is really the core foundation of what you need to know. So that's all I got for this week. I will have another one coming soon. So have a good one. Bye.